Welcome back to the Chem OG. Today I want to talk to you about ideal gases. And in order to properly discuss ideal gases, we have to define what they are and how it is that we call a gas ideal. And so an ideal gas has the following characteristics. One, each of the individual particles has zero volume. Now, straight away we can see that this is an unrealistic expectation because the only things that have zero volume are things that don't exist. And so when we say that the ideal gas particle has to have zero volume, there's no way that any particle has zero volume. Every particle takes up some sort of space. But the general principle is that the space that's occupied by that particle individually is very, very small compared to how far these molecules are away from each other. And a good way to think about that is to think about a very, very sparsely populated area. And so if you're ever driving through or walking through a sparsely populated area, there are barely any houses as you look left and right and into the horizon, right? Because all the houses are so far apart, that area is sparsely populated, it looks like no one lives there. And so when you take a look at how far apart these gas molecules are, they take up so much space collectively that it seems like, right, that there are no particles there. So each of the particles takes up zero volume relative to the great amount of space that they collectively take up. The molecules themselves experience zero interactions. And that's, again, ridiculous because all molecules experience at least some sort of London dispersion forces. And so saying that molecules experience zero interactions is unrealistic. But if we're saying that these particles are so far apart, and if we're saying that even when they do come in contact with each other, their interaction is very minimal, then all of a sudden this expectation becomes very close to reality. When those molecules do collide, those collisions are elastic, so no energy is lost. So when the two molecules collide with each other, just kind of bounced off each other, they merely change directions, but there's no energy lost in the form of heat or anything like that. So none of these three criteria is exactly realistic, but if we compare our calculations based on these three criteria with characteristics that we observe about gases in general, we will find that for certain sets of gases, those expectations align pretty darn well. And so we call those gas molecules ideal gases. Now these three bullet points right here comprise something that's called the kinetic molecular theory, and it describes gases that are very, very close to what we consider ideal behavior. To encourage this ideal behavior, what we want is we want gas molecules that are very far apart from each other. So that means we want low pressure, and we also want high temperature. That way, when the molecules do interact with each other, it's not a meaningful interaction, and it keeps our intermolecular interactions close to zero because they're moving so fast. So low pressure and high temperature are generally what we want in terms of forming gases in general. So when you think about ideal gases and the way to form them, think about what you would need in order to form the gas phase of any substance. So some examples of ideal gases include the noble gases, so helium, neon, argon, krypton down the line, hydrogen gas, nitrogen gas, oxygen gas, chlorine gas, bromine gas. We can include something like carbon dioxide in here as well. And so the larger the molecule gets, the more it separates from ideality, because the idea is to make sure that each particle has zero volume or close to it, and you want to minimize your interactions. So helium is a very, very ideal gas because its volume is very small and its interactions are also very minimal. So when we have an ideal gas, that ideal gas is going to obey something called the ideal gas law. And it's a law or an expression with which you're very familiar. PV equals nRT. And a lot of times when we talk about PV equals nRT, it goes hand in hand with a very specific set of circumstances known as STP. So STP is standard temperature and pressure. That temperature is 0 degrees Celsius, or if we measure it in the Kelvin scale, which we should, that's 273 Kelvin. Anytime you want to plug in temperature for PV equals nRT, you should always use the Kelvin scale. And pressure is going to be 1 atm, or we can put in other units like millimeters mercury or torr or pascals, depending on what it is that the problem stipulates. But we want the equivalent of 1 atm of pressure. And so at STP, if we plug in a temperature of 273 Kelvin here, if we use the ideal, or if we use the universal gas constant, if we use 1 mole for N and we plug in 1 atmosphere for pressure, the space that's occupied by 1 mole of an ideal gas is 22.4 liters. And you can also check out multiples as well. So for instance, 2 moles of an ideal gas would take up twice as much space, 44.8. A quarter of a mole of an ideal gas would take up 5.6, right? If you divide 22.4 by 4. And so depending on what situation you're looking at, right, this is a very good approximation that doesn't have you resorting back to plugging in the values individually every single time. Now, another way to take a look at STP is to say, well, the concentration then of an ideal gas under those conditions is, well, if 1 mole occupies 22.4 liters, we can think of using units of moles per liter or concentration instead. So moles over liters, 1 mole is equivalent to 22.4 liters. And so moles over liters is going to give us 1 over 22.4. When we have an ideal gas, we can make use of something called Dalton's Law. And Dalton's Law says that the sum of the individual partial pressures of gases that are in a mixture is equal to the total pressure. So if you want to find out the total pressure exerted by all the gases that are in a mixture, what you have to do is you take a look at the pressure that's exerted by each of these gases individually and you just add them up. Okay. Now at surface value, that makes intuitive sense. If you want the total pressure exerted by a bunch of gases, well, you think about the pressure that's exerted by one of them by itself, the second one by itself, and the third one by itself. And when you add them all together in the same container, their pressures should all add up. Now, yes, it makes intuitive sense, but the reason this law is significant is that when you start adding in more and more gases of a mixture, what you expect to also happen is that the amount of intermolecular interaction increases. And so I'll say that again, right? If you have a bunch of molecules pulled in together, they're going to start to interact. And as they start to interact, they're going to start interacting with each other, and they're not going to exert as much pressure on the walls of the container. And so when we measure total pressure, we measure it by taking a look at the pressure exerted on the walls of the container. If these molecules are busy interacting with each other, then what's going to happen under normal circumstances is that the pressure individually is going to start to decrease once you pile on more gases, and your total pressure exerted by all the gases is going to start becoming smaller and smaller relative to what you expect the total of the individual pressures to be. And so Dalton's law really only holds if all gases behave ideally. And a lot of times, depending on what gases we're looking at, that is indeed the behavior. So again, what makes Dalton's law significant is when you start adding gases together, you expect the total pressure to decrease as those gases start interacting more and more often. But what ends up happening is if all gases are behaving ideally, well, then you don't get that interaction. And so to go over some example problems here, let's take a look at our first one. Which of these two gases is larger, oxygen gas or argon? Okay, so if you take a look at atomic radii, you'll find that argon is going to be slightly larger than oxygen. But then again, we have 2 oxygen atoms, not just one, when we have molecular oxygen. So which one's which? And, for a lot of intents and purposes on an exam, right, you may not have a table of atomic radii. And so the question here is, which one is larger? Oxygen gas with its 2 atoms that are connected together, or argon, which is just 1 atom by itself? And the answer is, it's neither one. They're both the same size. Because the assumption when we're talking about gases is that these gases are behaving ideally, right? Remember that argon is a noble gas. O2 was an example of an ideal gas that we talked about earlier. So really all these gases actually have identical volumes, and that volume is 0. So neither of those gases, small as they are or large as they are, their volumes don't really matter, right, compared to the actual amount of space that they take up. So for all intents and purposes, right, 2 moles of oxygen gas is going to occupy the same space as 2 moles of argon. It doesn't really matter what the individual size of those particles is. So that's something you want to keep in mind, that all ideal gases have the same individual volume, and that's 0. How about this question? What is the partial pressure of helium that's contained in this mixture, right? You got 2 moles of helium, 3 moles of oxygen, and 5 moles of nitrogen, and we're keeping this at STP. So you're like, okay, well, if I have the amounts of each of these gases, I don't see anything that has pressure in it explicitly, right? There are no pressure numbers in terms of this question. But the fact that we're given that we're at STP means that we know what the total pressure is. And that total pressure at STP is 1 atm. And so because each of these gases depending on how much of each we have, contributes equally to the pressure, remember they're all the same size and they have identical behavior, it means that the partial pressure of helium is going to be dependent on how much of it we have relative to the total number of moles. So if we add up the moles here, we're going to get 2 plus 3, which is 5, plus another 5 gives us 10. So if our total number of moles is 10 moles, helium with its 2 moles is 1/5 of that amount. So if the total pressure is 1 atm, then the partial pressure of helium is going to be 0.2 atm, or 1/5 of an atm. Thank you so much for watching today's video. Please help support this channel by subscribing if you have not done so yet. And if you could take a look at the like button and tap it, that would be amazing. See you at the next video.